Algorithms in MATLAB. Pseudocode. Pseudocode is a high-level human-readable code that is often used to describe an algorithm or procedure. We use pseudocode in place of real code when we just want to express how something works without worrying about the actual implementation details of the code. The benefits of pseudocode are that they're easy to read and follow and can be quickly converted into any programming language. Recall the following question from the previous lab. Question 7. Write a function, number theory, which determines if a number is abundant, deficient, or perfect. A number is abundant if the sum of its proper divisors is greater than the number itself. A number is perfect if the sum of its proper divisors is equal to the number itself. Otherwise, the number is deficient. The input should be n, the number being checked, and the output should be either abundant if the number is abundant, deficient if the number of the factors is less than the number, or perfect if the factor sum is equal to the number. Now let's try to solve this problem first using pseudocode. So, for each number from 1 to n minus 1, if the number is a proper divisor of n, then we add the number to the current sum. And when we are done, if the current sum is greater than n, then we will return abundant. If the current sum is equal to n, then we will return perfect. If the current sum is less than n, then we will return deficient. Notice how I have described the algorithm that I will be using to solve my problem using simple English. The pseudocode, although it looks like MATLAB code, is actually not runnable in MATLAB. However, it's very similar, and I can quickly convert my pseudocode into actual MATLAB code. Now, let me actually write the MATLAB code. So function output equals to number theory. Except my output is output and my input is the number n. And then so I will keep track of my current sum. So current sum equals to 0. Now for each number from 1 to n minus 1, so for I is equal to 1 to n minus 1. If the number is the proper divisor of n, so I need to check whether or not I is the proper divisor of n. I can do that using the mod function. So if mod of n comma I is equals to 0, current sum equals to current sum plus I. So if the number is the proper divisor of n, I will add the number into my current sum. When I am done with my loop, I want to check the value of current sum and return either abundant, perfect, or deficient. So if current sum is greater than n, output equals abundant. Else if current sum is equal to n, output equals to perfect. And finally, if none of the above two are true, then the number has to be deficient. And there's my code. Notice how similar my pseudocode is with my actual implementation code. I have current sum, I have a for loop, I have an if else condition to test for these values. So this is how pseudocode is very useful for approaching problems. Pseudocode is very useful for modeling your solution and see how your code will execute. And then once you have your pseudocode, you can convert it into MATLAB code and run it to see whether or not it works. Okay, that's it about pseudocode. Linear search. Linear search is a simple algorithm that goes through every element in a list to find a particular value. So for example, given the following matrix here, so I have M, and I would like to find the index where the value 100 occurs. So here's the pseudocode for my linear search. Edit linear search. So for each item in the list, I want to check if the item is equal to the particular value that I'm looking for. And if it is, I want to stop my search and return the item's location. Otherwise, if by end of my loop I still have not found my item, I just simply return not found. So this will be the pseudocode for my algorithm. I basically go through every single item in my list, in my matrix, and check whether or not it exists. The item exists in my matrix. If it does, I return my index. If it doesn't, I simply return not found. Now let's see how I can implement this. Function index equals to linear search. So for my function, I will accept two inputs. One input is the matrix, and second input is the value that I'm looking for. Note that we are going to be using -1 to denote that the value is not found. So I start off by setting index into -1. Now for I is equals to 1 to the length of my matrix. So I will be looping through every single value in my matrix. If the element of the matrix I index I, so matrix I is equals to the value that I'm looking for, then I'll set my index to I, and I will break and jump out of my loop. And that's it. So this is my linear search. So what my linear search function does is it takes a matrix and takes a value and look for the index where the value occurs. If the value does not exist, it simply returns -1. Let's see how this works. Linear search M, let me look for the value 100, and gives me the answer 5. So it's located at index 5. This is 1, 2, 3, 4, 5. If I would like to search for the value 15, it should give me 2. If I look for another value, if I want to find a value that does not exist in my matrix, it should give me -1. So let's look for the value 99. And there, it gives me the position of -1. So this is a very, very basic algorithm in MATLAB. It's very intuitive. You just simply go through your values one by one until you find the value that you're looking for. So that's linear search. Now let's look at a more complicated algorithm. This algorithm falls into the family of sorting. So bubble sort. Sorting a list is a very common scenario. So given the following list here, M is equals to 5, 1, 12, -5, and 16. So given my matrix here, I would like to sort my matrix so that they are in increasing order. Now how will we do this? Well, we will approach this problem using bubble sort, a very elementary sorting algorithm. So edit bubble sort. So let's first write the pseudocode for bubble sort. So from 1 to the length of the array or matrix, and for each element in the array, if the current element is greater than the next element, then we'll simply swap their values. So this is a very, very simple algorithm that allows us to store matrices. So bubble sort operates on a very simple principle. At each step, the larger values float to the top like bubbles. The algorithm repeatedly steps through the array, check the adjacent elements of the array, and if they're in the wrong order, swap them. Swapping is done by using a temporary variable to hold the first element, set the value of the first element to the second, and set the value of the second back to the temporary variable. So let's look at an example of how bubble sort works. So initially I have my matrix 5, 1, 12, -5, and 16. I start off at my first value here. I compare it to my second value. Since 5 is greater than 1, I will swap these two. And now I am here. 1, 5, 12, -5, 16. And then I compare the next two values, 5 and 12. Because 5 is less than 12, nothing happens. And then now let's look at my third value, third pair of values, 12 and -5. Because 12 is greater than -5, 12 and -5 are swapped. So now we end up here. And 12 compared with 16, and since 12 is less than 16, there's no swapping. So this is the result after one for loop run. Now we run our loop again. 1 is compared with 5. Since 1 is less than 5, there is no swapping. 5 is compared with -5. And because -5 is less than 5, we have a swapping here. Now we end up with 1, -5, 5, 12, and 16. 5 is less than 12, so there's no swapping, and 12 is less than 16, so there's no swap. Now, in our third run of our for loop, we have 1 compared with -5. And because 1 is less than -5, we will swap -5 and 1. And then we have -5, 1, 5, 12, and 16. In our another for loop, we compare -5 and 1, 1 and 5, 5 and 12, 12 and 16, and there's no changes. Once there are no changes, we know that we're done with our sort, and we'll simply stop. So this is how bubble sort works. Now, given our pseudocode here, let's try to implement the above algorithm in MATLAB. So function A is equals to bubble sort of the matrix M. So first thing I want to do is copy M into my new matrix A, because I do not want to modify my original matrix. So A is equal to M, and we will be working with A the entire time. Now, for I is equals to 1 to the length of A, which is basically this line here, from 1 to the length of my array. And then I have another for loop for each element in the array. So for, let's say, J is equals to 1 to the length of A minus 1. Now we want to check if the current element is greater than the next element. The reason why we have minus 1 here is because we'll be accessing the last element. So there's no need to go to length of A. We just need to go up to length of A minus 1. So if A at J is greater than A at J plus 1, so if the value at the current element is greater than the next element, then we would like to swap these values. To swap, we use a temporary variable called temp. So temp is equals to A of J plus 1. And then we set A of J plus 1 equals to A of j, and then we set A of j equals to the value of temp. And we're done with our loop. And this is it. This is bubble sort. Notice how similar our pseudocode is with our actual implementation. So we have two loops. Our first loop goes from 1 to the length of A, which is from 1 to the length of my array. Then my second loop goes from 1 to the length of A minus 1, which goes through every single element in the array. Then, if the current element, which is AJ, is greater than the next element, which is J plus 1, we swap their value, which is down here. So this is how bubble sort works. Now, just to see the steps of bubble sort, let me add A here, so that we can see what happens when our function runs. So bubble sort A is equal to bubble sort of M. Notice our matrix A at the end of each for loop. So we start off with 5. We start off with 5, 1, 12, negative 5, 16. 5, 1, 12, negative 5, 16. After our first for loop, we have 1, 5, negative 5, 12, 16, which is here. After our second run, we have 1, negative 5, 5, 12, 16. After our third run, we have negative 5, 1, 5, 12, 16. Negative 5, 1, 5, 12, 16. And then we look at our last one. We have negative 5, 1, 5, 12, 16. So this, at this point, is our final answer. We have already sorted our loop. The reason why we have the same value being shown multiple times is that our function, our bubble sort, is not as efficient as we would like. We're not checking the case where our matrix is already sorted and quit prematurely. So this is the reason why we're still repeating a few times. However, as we can see, our function works as we're expected. Our matrix becomes sorted, negative 5, 1, 5, 12, 16. And this is how you implement bubble sort.